Welcome to this fascinating exploration of thermal behavior in microfluidic systems. Today we're going to uncover a mystery that puzzled researchers for years. Why do microchannels exhibit unexpected thermal patterns? Let's start with the traditional understanding. In macroscopic systems with laminar flow, we expect smooth, predictable temperature profiles. Laminar flow occurs when fluid moves in smooth parallel layers. There's no turbulent mixing, so we expect orderly thermal behavior. Here's a typical laminar flow in a channel. The velocity profile is parabolic, with fluid moving fastest at the center and slowest near the walls. We would expect the temperature to vary smoothly as well. The classical heat diffusion equation suggested that with uniform heating, the temperature should be smooth and predictable throughout the channel. This is the heat equation. Rho C sub P times partial T over partial T equals K times the Laplacian of T. Here, Rho is density, C sub P is specific heat, K is thermal conductivity, and T is temperature. For steady-state conditions with uniform heating, this equation predicts smooth temperature distributions without localized hot or cold zones. But when researchers began experimenting with microchannels, they discovered something unexpected. Even with uniform heating, experiments revealed localized hotspots and cold zones that shouldn't exist according to classical theory. Researchers observed these irregular thermal patterns. Red regions represent hot zones, blue regions represent cold zones. This was completely unexpected for laminar flow with uniform heating. This observation directly contradicted what classical fluid dynamics and heat transfer theory predicted. Something was missing from our understanding. So the question became, what physical mechanisms could create these localized thermal gradients in what should be a thermally simple system? To understand the puzzle, we need to look at the Reynolds number in microfluidic systems. The Reynolds number is defined as RHO U d sub h divided by mu, where U is velocity, d sub h is hydraulic diameter, and mu is dynamic viscosity. In microchannels, the hydraulic diameter d sub h is extremely small, typically tens to hundreds of micrometers. This makes the Reynolds number very low. For typical microchannels with hydraulic diameter around 100 micrometers, the Reynolds number is usually less than 100, confirming laminar flow. The low Reynolds number definitively confirms laminar flow conditions. Yet the thermal anomaly still appeared. This deepened the mystery. The first clue to solving this mystery came from viscous dissipation. This is a phenomenon that becomes important at small scales. Viscous dissipation occurs when internal friction in the fluid converts kinetic energy into thermal energy. In bulk systems, this effect is negligible. The viscous dissipation rate is given by phi equals mu times the quantity partial U over partial Yn quantity squared. This represents the power per unit volume generated by viscous friction. In laminar flow through a channel, the velocity gradient partial U over partial Y is largest near the walls where the fluid transitions from moving to stationary. This diagram shows the parabolic velocity profile in a channel. The red regions near the walls indicate where velocity gradients are highest, leading to maximum viscous dissipation and localized heating. Now, you might ask, how significant is this viscous dissipation effect? Is it really enough to create noticeable temperature variations? To answer this, we use a dimensionless number called the Brinkmann number, which quantifies the importance of viscous heating relative to conductive heat transfer. The Brinkmann number is defined as mu U squared divided by K delta T, where delta T is the imposed temperature difference. When the Brinkmann number approaches or exceeds unity, viscous heating becomes comparable to conductive heat transfer and cannot be neglected. Let's do a numerical estimate. Consider water flowing at 1 meter per second with viscosity 10 to the minus 3 Pascal seconds and thermal conductivity 0.6 watts per meter Kelvin. For a temperature difference of 10 Kelvin, the Brinkmann number is approximately 0.0002. This seems small, but in microchannels with high velocities it can become significant. In microchannels operating at high flow rates, especially with viscous fluids, the Brinkmann number can exceed 0.01, making viscous dissipation a measurable contributor to thermal patterns. The second clue came from understanding thermal boundary layers at the microscale. These layers behave very differently in small channels. The thermal boundary layer is the region near the wall where temperature adjusts from the wall temperature to the bulk fluid temperature. The thermal boundary layer thickness delta sub T scales as K divided by ratio C sub Pu. Notice it depends inversely on velocity. In microchannels, the thermal boundary layer thickness can become comparable to or larger than the channel dimensions. This means the entire channel is essentially a boundary layer. In this microchannel with hot and cold walls, the thermal boundary layers shown in red and blue extend across the entire channel height. There's no bulk region unaffected by the walls. The Peclet number tells us whether heat transport is dominated by fluid motion or by thermal diffusion. The Peclet number is U d sub h divided by alpha, where alpha equals K over rho, C sub P is the thermal diffusivity. Interestingly, the Peclet number equals the Reynolds number times the Prandtl number. For water, the Prandtl number is about 7. When the Peclet number is low, thermal diffusion is strong relative to advection, leading to thin but highly active thermal layers near channel walls and corners. The third and critical clue involved channel geometry. The shape of microchannels creates unexpected thermal concentration effects. Sharp corners, abrupt changes in cross-section, and geometric discontinuities create regions where thermal gradients become extremely large and localized. This shows a microchannel with a sudden contraction. The red dots at the corners represent localized hotspots where thermal gradients concentrate due to geometry. Even in laminar flow, geometric features can create small recirculation zones where fluid gets trapped. These zones develop different thermal signatures than the main flow. The surface area to volume ratio in microchannels scales as 1 over d. As channels get smaller, surface effects become dominant over bulk effects. The surface area to volume ratio is approximately 1 over d sub h. For a 100 micrometer channel, this ratio is 10,000 per meter compared to 100 per meter for a 1 centimeter channel. Now let's put all three clues together to see the complete picture of microscale thermal behavior. First, viscous dissipation creates localized heat sources, preferentially near the walls where velocity gradients are highest. Second, thin thermal boundary layers mean that these localized heat sources create large temperature gradients over very small distances. Third, the channel geometry determines exactly where these effects concentrate, creating the observed hot and cold zones. This illustrates the coupled effect. Red circles show viscous heating concentrated near walls. Green lines represent the steep thermal gradients that develop in the thin thermal boundary layers. To capture these effects mathematically, we need a modified energy equation that includes viscous dissipation. The complete equation is RHO C sub Pu times partial T over partial X equals K times the Laplacian of T plus phi, where phi is the viscous dissipation term we saw earlier. The phi term representing viscous dissipation is the key addition that was missing from classical heat transfer theory. This term is negligible in bulk systems, but crucial at the microscale. The full expression for phi involves summing the squares of all velocity gradients. This captures how shear in any direction contributes to heating. Let's do some numerical estimates to see how much temperature rise we can expect from these effects. Consider water flowing at 10 meters per second through a 50 micrometer channel. This is a high but achievable flow rate in microfluidics. The velocity gradient near the wall is approximately u divided by d sub h over 2, which gives 4 times 10 to the 5 per second. The viscous dissipation rate is 10 to the minus 3 times this gradient squared, giving 1.6 times 10 to the 8 watts per cubic meter. This corresponds to 160 kilowatts per cubic meter of volumetric heat generation. That's an enormous heating rate concentrated in a tiny volume. The resulting temperature rise is approximately phi d sub h squared divided by K, which gives about 0.7 Kelvin. This is easily measurable. Over the length of the channel, the cumulative effect of this heating can produce temperature rises of several degrees, creating the observed thermal patterns. So how did researchers validate this theoretical understanding? They used sophisticated experimental techniques. Researchers embedded microthermocouples at specific locations within microchannels to directly measure local temperatures. Infrared thermography provided full-field surface temperature maps, revealing the spatial patterns of hot and cold zones. When viscous dissipation and thin boundary layer effects were included in the models, the predictions matched experimental observations remarkably well. This comparison shows the difference. The left panel shows classical predictions of uniform temperature layers. The right panel shows the new model capturing localized hot and cold zones, matching experiments. Understanding these thermal effects has profound implications for designing microfluidic devices. Engineers can no longer assume uniform temperature distributions when designing microfluidic systems, especially those involving chemical reactions or biological samples. Effective thermal management requires explicitly accounting for localized hotspots that can damage temperature-sensitive materials or affect reaction kinetics. Optimizing flow rates becomes a balance. Higher flow improves mixing and transport, but increases viscous heating and thermal gradients. Let's look at a concrete application. Polymerase chain reaction, or PCR, in microfluidic chips used for DNA amplification. PCR requires precise thermal cycling between 95 degrees for denaturation and 55 degrees for annealing. Temperature uniformity is critical for efficiency. This shows temperature variations in a microfluidic PCR chamber. Even with nominal 95-degree heating, viscous dissipation and geometry create zones ranging from 92 to 97 degrees, affecting reaction efficiency. Localized hotspots exceeding 97 degrees can denature the polymerase enzyme, while cold zones below 93 degrees reduce reaction rates, both lowering PCR yield. The solution involves designing channels with geometries that minimize viscous dissipation, using lower flow rates where possible, and implementing active cooling in critical regions. This story reveals a profound lesson about microscale physics. Hidden structure emerges when we shrink systems. Nature contains hidden structure at every scale we examine. As our experimental capabilities improve, we continue to discover new phenomena. The microscale sits in a fascinating regime between classical bulk behavior and quantum molecular behavior, where both worlds meet and interact. Future technologies in medicine, energy, and information processing increasingly depend on understanding and controlling these microscale thermal phenomena. The resolution of this thermal mystery has enabled the design of better microfluidic devices for diagnostics, drug delivery, and chemical synthesis. Thank you for exploring the fascinating world of microscale thermal physics with me today. I hope this has given you a deeper appreciation for the hidden complexity in seemingly simple systems.